Let's see how to extract possible execution time functions from simple program snippets. We will step through several examples. In each example, we try to determine the number of computational steps that are executed by an algorithm depending on the input size. That can then be described in the form of a function, the execution time or runtime function. In the first example, all elements of an array are set to 0. The input is the array with n elements. Each element is an integer. Therefore, the size of the input is the amount of memory it takes to store n integers. In Java, a single integer requires 4 bytes, but in a different language, the number of bytes might be 2 or 8, for example. The important point is that the input size is n times some constant. We don't know what the constant is. That is implementation dependent. We assume here for simplicity that the constant is just 1, thus the input size is n. Now we have to count the number of computational steps. The variable I is set first to 0, that is 1 step. In each loop iteration, an array element is set to 0 and I is incremented by 1. So an individual iteration takes 2 steps. How many loop iterations are performed? When I reaches the value n, then the loop terminates. As I starts with 0, the loop body is executed n times. Finally, let's not forget the Boolean expression I less than n that is evaluated before each iteration, and then one more time when I reaches n and the loop terminates. Thus the comparison is evaluated a total of n plus 1 times. In summary, the number of steps is 1 plus 2 times n plus n plus 1, which is 3 times n plus 2. Finally, we can describe the execution time function. Typically, I call that function t. T stands for time. Remember, we measure the number of steps in the input size n. So t of n is 3n plus 2. Here's an even simpler looking example. The input is again an array. The program itself consists of a single line which assigns the average of the first and last element of the array to n. We assume again that the input size is just n, as the input array has n elements. There's only one instruction. Thus you could say that the number of computational steps is 1, and that is perfectly fine. However, you could also argue that we need to perform an addition and a division. So you could argue that we actually need 2 computational steps. Which way to count is correct? Well, we will see later that it does not matter if we count the instruction as 2 steps or just as 1 step. So let's stick with 1 step. Then the execution time function t of n is 1. Note that it does not matter how many elements the array has. The program performs just 1 instruction irregardless of the input size. Let's take a slightly more complex example with nested loops. The input is the same as in the previous 2 examples, thus the input size is n. Let's start counting the computational steps. The counter I is set once to 0. I is incremented n times. The comparison I less than n is executed n plus 1 times. The body of the outer for loop is executed n times. Each time we have the same number of steps that are executed. This number of steps for a single iteration is as follows: 1 step for initializing j, n steps for incrementing j, n plus 1 steps for the loop condition. And then the array element at index I is updated n times. Did you take notes? Well, if not, here's the calculation we came up with. The number of steps is 1 plus n plus n plus 1 plus n times 1 plus n plus n plus 1 plus n, which is equal to 3n squared plus 4n plus 2. The execution time function can be defined as t of n equal to 3n squared plus 4n plus 2. Now that was a lot of work. A lazy person might just see that there's a single instruction in the body of the inner for loop and counts only how often that instruction is executed overall. We know it's executed n squared times. Then that lazy person might argue the execution time function is just n squared. Later on, we will see that this is actually fine. The important part here is that the execution time function is quadratic in the input size n. In the next example, the input is a stack of book objects. What is the input size? Well, the input size is the number of elements in the stack. Let's give the input size a name. Computer scientists typically name the input size n, however you could name it differently. The while loop keeps printing the book on top of the stack and then removes the top element. Thus the loop body is executed n times, each time executing 2 instructions. The while loop condition is checked n plus 1 times. Thus the overall number of steps is 3n plus 1. The runtime function t of n is 3n plus 1. The next example is a little tricky because the input is a 2-dimensional array with m times m elements. So the input size is m squared. Now let's do a lazy count of the number of steps. First, the variable sum is set to 0. That is one operation. The inner loop body contains a single instruction and is executed m squared times. We will neglect all the other operations that handle the counters I and j, for example. This is okay, as we will see later. So the number of computational steps is m squared plus 1. Remember, the execution time function is a function in the input size, which is m squared. So we might want to write that t of m squared is equal to m squared plus 1. That is not completely wrong, but the argument of the function t should be a simple variable, not an expression in m like m squared. So we have to do a little variable replacement. Let's give the input size another name, say n. So n is equal to m squared. We replace the occurrences of m squared by n in the function and get t of n is equal to n plus 1. So the number of computational steps is linear in the input size. Let's go back to selection sort. Here again the input is an array with n elements. The loop body of the outer for loop is executed n times. Each time min is set to I. That is one operation in each iteration of the loop body. Also, the last operation is performed once in each iteration of the loop body. Now let's look at the inner for loop. The for loop inside the loop body iterates at most n times. In fact, it iterates at most n-1 times. The exact number of iterations depends on the value of I. The first time I is 0 and therefore j is initialized to be 1. So the if statement is executed n-1 times. Next time I is 1 and j is initialized to be 2. So the if statement is executed n-2 times. Then I is 2 and j is set initially to 3 and the if statement is executed n-3 times, and so on. Let's assume the if statement requires one computational step. Then for the first iteration of the outer for loop body, we have to add n-1 steps for the inner loop. For the second iteration of the outer loop, we have to add n-2 steps for the inner loop, and so on, all the way down to 1. So overall, the execution time function is t of n equal to n times 1 plus 1, plus n-1, plus n-2, plus n-3, and so on until we reach 1. Let's simplify that expression a little bit. If you add the numbers n-1, n-2, n-3 all the way down to 1, that is equal to n-1 times n over 2. If we plug that in, then we get t of n is equal to a half n squared plus 3 half n. Let's move on to bubble sort. The input size corresponds again to the number of elements in the array that is passed in, so the input size is n. The number of executed steps corresponds to the number of times the innermost if statement is executed. The outermost for loop iterates n-1 times, since the counter starts at n-1 and the for loop terminates when I has reached 0. In the first iteration, the nested for loop iterates n-1 times as j starts at 0 and terminates when it reaches I, which is n-1 in the first iteration. So in the first iteration of the outer for loop, the if statement is executed n-1 times. In the next iteration of the outer for loop, I is n-2, and so the if statement is executed only n-2 times. Next time, the if statement is only executed n-3 times, and so on, until the if statement is only executed once in the last iteration of the outer for loop. In summary, the number of computational steps is n-1 plus n-2 plus n-3 and so on, all the way down to 1. We have seen before that this sum is equal to n-1 times n over 2, or equivalently a half n square plus a half n. The last example is insertion sort. The number of steps depends basically on how often the second and third line are executed and how often the last 3 lines are executed. As far as the first 2 lines are concerned, that is not a problem. The for loop iterates exactly n-1 times. So these 2 instructions are executed n-1 times altogether. But how about the last 3 instructions? That depends on how the items in the given array are arranged. Imagine the array is already sorted, then the body of the while loop will never be executed. On the other hand, if the array is sorted in reversed order, then the element to be inserted has to move up each time to the first position in the array. That is the most time-consuming case. So in that case, the while loop iterates once in the first iteration of the for loop. Then it loops twice in the second iteration of the for loop, then 3 times, and so on until it loops n-1 times in the last iteration. So in the worst case, the 3 steps in the while loop are executed once plus 2 plus 3 and so on until n-1 times. We know adding the numbers n-1, n-2 to 1 is equal to n-1 times n over 2. Then we get for the execution time function t of n is equal to 2n for the first 2 instructions in the for loop plus 3 n-1 times n over 2 for the 3 instructions in the while loop. Note that we here have focused on the worst case where the elements are arranged in reversed sorted order in the beginning. That's because you typically want to give a guarantee as to how many steps an algorithm takes at most.